Today we can discuss the properties of colloids. The properties of colloids are very important. When we study the properties, we can identify a lot of applications of these colloids. The first one, colligative properties. What are colligative properties? Colligative properties are the properties of dilute solutions. Properties of dilute solutions, which depends only on the number of particles present in the solution. That is colligative property. And colloids, we cannot call it as a true solution, but they also will show colligative properties. The number of particles in a colloidal solution is comparatively small as compared to a true solution. We know colloidal particles are comparatively bigger in size, more than 1 nanometer, but solution less than 1 nanometer. And therefore, the number of particles will be less than that in the case of true solution. So the colligative properties are of small order as compared to values shown by true solutions of same concentration. So colloids also will show colligative property, but the values are of a small order. That you have to remember. Next one, important property, Tyndall effect. Tyndall effect. What is Tyndall effect? You can see some examples of Tyndall effect here. When light enters into a dark room, the path is visible. The path is visible. That is due to Tyndall effect. Tyndall effect. In a room, there will be a colloid due to the dispersion of dust particles in the air. So when light enters into a dark room, the path is visible. That is due to Tyndall effect. Here you can see when light enters through the leaves, in between the leaves, the path is visible. That also due to Tyndall effect. Here also there will be dispersed dust particles, and due to this dispersed dust particles, the path is visible. Here, a beam of light in a dark room, you can see, clearly you can see, it is under smoke, a small smoke is there. When light is passed through the smoke, the path is clearly visible. You know, smoke is a colloid. So when light passes through the colloid, the path is clearly visible. That is Tyndall effect. So what is Tyndall effect? When light passes through a colloid, its path is visible. And why this path is visible? Because the light is scattered by colloidal particles. The light is scattered by colloidal particles. So Tyndall effect, the scattering of light by colloidal particles, and as a result of this scattering, the path of light is visible when light is passing through a colloid. Here you can see a figure in which light is passing through a colloidal solution from a source, and a lens is used, and the converged light is passing through the solution. And the converged light is passing through the solution, you can see the path. In this part, the path is visible like a cone, and therefore it is known as Tyndall cone. And that is due to scattered light. From where it is observed? From a perpendicular direction it is observed. So that is Tyndall effect. Scattering of light by colloidal particles is known as Tyndall effect. The path of the light is visible by a bluish light when viewed light at right angles to the passage of the light. That is, when we observe it from the top, it will appear as a bluish light. The bright cone of the light is called Tyndall cone. But to observe this Tyndall effect, there are two conditions. The first one is the diameter of the dispersed particle should be almost equal to the wavelength of the light used. The diameter of the dispersed particle is almost equal to the wavelength of the light used. The light passing through the colloid, it has a wavelength. That wavelength should be almost equal to the radius of the particle present in the colloid. So there should not be a larger size difference, almost equal. That should be almost equal. Then only you can observe Tyndall effect. The refractive indices of the dispersed phase and dispersion medium differ greatly in magnitude. Then only you can observe Tyndall effect. Refractive indices should be different. Refractive indices of dispersed phase and dispersion medium. If it is different, you can observe Tyndall effect. So these are the two conditions. Which are the two conditions? The diameter of the dispersed particle is almost equal to the wavelength of the light, and the refractive indices of the dispersed phase and dispersion medium should be different. These are the two conditions. And based on this Tyndall effect, a scientist, Sigmundi, in 1903, set up an apparatus known as ultra microscope. So Tyndall effect is used in the working of ultra microscope. That is the importance of Tyndall effect. Another important property of colloid is the color of colloid solutions. Colloidal solutions have characteristic color. And this color of colloidal solution depends on various factors. The first one is wavelength of the light. And the second one is the size and nature of the particle. And the third one is the manner in which the observer receives the light. That means from which direction it is observing. So there are three important factors which affect color of a colloidal solution. What is the first one? Wavelength of the light. First one, wavelength of the light. What is the second one? Size and nature of the particle. Size and nature of the particle. And the third one, the manner in which we observe the light. Whether we are observing it perpendicularly from the top, or we are observing the transmitted light, that also decides the color of the colloid. You will understand it from the examples. For example, a mixture of milk and water appears blue when viewed by the reflected light. If you are viewing the reflected light, that will be blue. Means if you are observing it in a perpendicular direction, from the sides, if you are observing it from the sides, the light will be blue, or in a perpendicular direction. But when you view the transmitted light, it will appear as red. If you are observing the transmitted light, if you are standing opposite side of the light, you can see it in red color. Similarly, in the case of gold salt, the finest gold salt means size of the particle is very small. Finest gold salt is red in color. As the size of the particle increases, it appears purple, then blue, and finally golden. So these are some of the examples to understand the color of colloids. That depends on various factors, mainly three factors. You may remember it. Now the next one, Brownian movement. The dispersed particles will collide with the molecules of dispersion medium. And due to this collision, the dispersed particles will be in continuous zigzag movement. And that continuous zigzag movement is known as Brownian movement. And the name is from Robert Brown. He is a botanist, and he's observed this kind of motion in pollen grains when they are on the surface of the water. When colloidal solutions are viewed under a powerful ultra microscope, the colloidal particles appear to be in a state of continuous zigzag motion all over the field of view. And this motion is known as Brownian movement. And what is the reason for this Brownian movement? The reason for the Brownian movement is unbalanced bombardment of the particles by the molecule of the dispersion media. Unbalanced bombardment of the particles with the molecules of the dispersion media. The dispersion molecules of dispersion medium are in continuous motion. They will collide with the dispersed particles, and the collision may not be balanced. Therefore, in one direction it will move. And what is the advantage of this Brownian movement? Because of this continuous motion, this Brownian movement does not permit the particles to settle. Settling of colloidal particles will not take place due to this Brownian movement, and thus is responsible for the stability of salts. Therefore, Brownian movement helps to stabilize colloidal solutions. Another important property, the colloidal particles are charged. The particles have a particular charge, either positive or negative. Charge on colloidal particles. When we analyze colloidal solutions, we can see the colloidal particles are charged. The colloidal particles always carry a charge. And if you analyze, you can see all the dispersed particles have same charge, similar charge. If one of the dispersed particles is positive, all other particles will be positive. And what is the advantage of this charge? Because of this charge, further union or further combination of the particles not possible. Since they are not combining together, the settling will not take place. Positively charged particles will repel each other. Negatively charged particles will repel each other. Therefore, they cannot combine together to form particles of bigger size. That means more than 1000 nanometer. Therefore, it will not settle down. So, charge on colloidal particles provides stability. Brownian movement provides stability, and this charge on colloidal particles also provides stability. How the colloidal particles are developing this charge? The charge on the salt particle is due to electron capture by the salt particles during electrode dispersion of metals. Electrode dispersion, Bradick's arc method, you may remember, Bradick's arc method. And during that process, the capturing of electrons may take place by the particles. Otherwise, in the case of ferric hydroxide, in the preparation of ferric hydroxide, a lot of electrolytes are present in the solution. So preferential adsorption of ions from the solution, that is another possibility. Or maybe due to the formation of electrical double layer. What is electrical double layer? That we can see in the next class. And here some examples for positively charged salts and negatively charged salts are given. Examples for positively charged salts: hydrated metallic oxides, Fe2O3 XH2O. Hydrated metallic oxides, basic distabs, an example methylene blue. Hemoglobin, oxides, example TiO2. So metal oxides, basic distabs, hemoglobin, oxides. The same time negatively charged metals, copper salt, silver salt, gold salt, all are negative salts. Metallic sulfides, arsenious sulfide, antimony Sb2, antimony sulfide, cadmium sulfide. All these are examples of negatively charged colloids. Acid distabs, example EOC, that is a negative colloid. Salts of starch, gum, gelatin, clay, charcoal, all these are examples of negative colloids. There is no general classification, depends on various factors, so we cannot predict, but generally we can say metallic oxides are generally positive. Hydrated metallic oxide means hydroxide, FeOH thrice, that is a positive colloid. Hydrated metal oxides means hydroxides also positive, but metal salts are negative. Okay, I think it is enough for today. We can continue the remaining parts in the next class.